Good morning everybody. Yeah, the last lecture I have talked about the location of nozzles, how if they are not proper, what difficulties it can create. Yeah, I was in the last lecture I was talking about this, that if the nozzles are not properly placed or if the nozzles are not functioning properly, then what difficulties it can create. I had mentioned there that overlapping is very important. If there is overlapping, then only there is uniformity of cooling throughout the surface, that is important. Throughout the surface there should be overlapping of water sprays, and that will lead to uniformity of temperature. So, the shape will be okay, cast product, possibility of stress generation will not be there or within control. So, possibility of crack formation also will not be there. So, today let us see another thing, like suppose I have talked about, I have shown you the layout of the nozzles, and what happens in reality is we are casting say different width of cast product, say slab, let us talk of slab. Sometimes we may cast a slab which is as wide as say 1300 millimeter, 1.3 meter. Next maybe we have to cast 1100 millimeter, that means 1.1 meter. Sometimes maybe we have to cast 900 millimeter, that means 0.9 meter. So, in the same caster, when you are casting slabs of different width, you can imagine what will be the problem. Like say, let us come to a situation where we are casting say maximum width say 1300 millimeter. So, we must have nozzles, different nozzles, so that we can get water spray from one end of the broad face to the other. That means throughout the surface cooling has to be there, is it not? That is the purpose. The whole surface, that means whole broad surface should be cooled uniformly. So, the nozzle arrangement should be such, the staggered multi nozzles, we have called it, different nozzles are there and they are staggered. You see here these blue ones, these dark blue ones, 1, 2, 3, 4, 5, they are covering the whole width and there is also overlap. Now, just behind at the back we have 1, 2, 3, 4 which can do some at position at a staggered position. Now, when we are using the maximum width, this front row suppose is being used of the nozzles. Next, when you are going to the width of intermediate dimension, say from 1300 we have gone to 1100 millimeter, then what is happening? This two extremes we have stopped using. Why? Because otherwise the amount of water, if you use these two also, this will be of no use. First, because it is falling outside the width, that means beyond the broad surfaces, number one. Number two, the water, the whole water is getting distributed. So, here water, relative amount of water is being less. So, instead what we want is outer nozzles, these two outer nozzles should not be used when you are using a slab of intermediate width. So, what problem it can have? Number one, it is mentioned here that large underspraying can be problematic, especially in upper cooling zones. What is happening here is we are not using this. So, there is a possibility of underspraying in certain extreme areas. So, what can happen when you are in the upper cooling zone? Upper cooling zone means you have just come out of the mold. So, lot of cooling is necessary, and intensity of cooling is relatively more, because excessive heat is there inside the strand. So, we want large amount of cooling so that the temperature comes down, temperature of the strand, and the shell thickness increases. So, now in such case if you have stopped using this nozzles, two extreme nozzles. Sometimes it can create underspraying. What does underspraying means? The amount of spraying what we are doing is relatively less. First, what I have told you is we are using staggered multi nozzles, one layer of nozzles here, another layer at the back, say just beneath behind it, and all together we are putting lot of water. So, finally, the amount of water is quite uniform here, but what is happening here is the two extreme we have stopped using, this one and this one, because we do not need it. So, in such case, particularly in the upper segments, upper cooling zones, there may be underspraying, that means we are not utilizing to the fullest extent, that may be a problem. Okay, the shell thickness is not increasing to the desired extent, that the extent of bulging possibility will be there. Okay. Now, let us come to another situation. We are using a minimum width, that means maybe we have come down to a 900 millimeter width now of slab. So, what happens? You are using only these nozzles, these extreme nozzles we have stopped using. So, inner nozzles we are using, outer nozzles we are not using. So, what we do? We use air purging from outer nozzle. We are not using water, we are not spraying water from the outer nozzles, we are spraying air to get a uniform cooling. Here also intermediate width outer nozzles off, only say two extremes, air purging for outer nozzles. So, what I am trying to harp upon is that you can control the width of the spray depending on what is the width of your slab. If you are using very wide slabs, you use the whole spray width. If you are using a narrow slab, relatively less wide slab, you can use narrow or intermediate width spray, but for that you must have separate control of water on the sprays. That means you can stop water flow in the extreme nozzles. Here also you can stop water flow in the next to next one, this one you have stopped, this one also you have stopped. Earlier you have stopped these two, now you have stopped these two. So, individual water control in each and every nozzle is a must, is a requisite, is essential for such spray width control. So, we have to remember when we are casting slabs of different width, we must have this facility in secondary cooling zones. That means the control of water for the different nozzles arrayed at different locations must be different. We must have a separate control, so that from wider when you are going to intermediate or narrow width slabs, we can consequently control the width of the spray. That is what is important. Okay, now let us see another important aspect. What is meant by nozzle alignment? Here I have earlier discussed that in between the two rolls we have a nozzle and the spray is coming and impinging on the strand surface within this area. That means in between the space of two support rolls we are using the water spray. So, here what is happening? It is no problem, it is an uniform spray, no misalignment, nozzle is correctly aligned, the spray is falling in a desired fashion on the surface. Look at here. Here what is happening? There is a misalignment. The location of the nozzle should have been here. Instead of that, the location is here. So, what is the consequence? Consequence is the spray is not fully impinging on the strand surface, number 1. Part of the spray is getting distracted or not falling at all. So, what is happening? Here there is no water, here there is less water. So, because of misalignment, because of the misaligned nozzle, the water intensity is low. Because of this, heat transfer will be low, cooling also will be low. So, what is the consequence? Consequence will be higher bulging, the more probability of bulging, possibility of thermal strain getting generated. Why? Because here there is no cooling, here there is some cooling. So, non-uniform cooling. So, there is a possibility of thermal strain, possibility of internal or surface defects. Why internal defects? There is a possibility of bulging here because it is less. So, bulging will create internal crack. Also because of non-uniform cooling, there may be reheating cracks on the surface. So, possibility of internal or surface cracks. Here if you have a correctly aligned nozzle, no whatever designed water intensity you have intended or you have the plan, the same thing is falling on the impinging on the strand. So, heat transfer is also whatever you have desired, the cooling also whatever you have desired. So, the cooling is uniform, heat transfer is uniform, there is no possibility of either bulging or heating cracks, so everything is fine. So, misalignment of nozzles can create this problem. Earlier I have talked about, you remember, earlier I have talked about non-functional of nozzle. This nozzle was not functioning. So, that was creating non-uniformity, non-uniform temperature distribution, possibility of reheating, possibility of shape change because of stress generation. So, that was one problem. Some nozzle was location was there, okay, but it was not functioning. So, non-functional nozzle created non-uniform cooling. But now what I have been talking is misalignment of nozzle. Nozzle is there, it is functioning also, water is coming out, but it is misaligned. It is not located at the desired position, it has shifted. Nozzle location due to some mechanical problem, it has shifted. So, the consequence is only part of the water, whatever water we had intended to impinge on the strand surface, only part is falling, other part is not falling, and that too it has shifted the location. It was supposed to be from here to here, so only what we are getting is only here to here. So, the whole surface is not getting water and it is getting less water also. So, lower intensity, non-uniform intensity. So, less cooling, less non-uniform cooling, so possibility of bulging, possibility of because of non-uniform cooling and less cooling, possibility of thermal strain, and as I have told you, possibility of reheating. So, because of reheating there will be a tensile strain on the surface and crack generation. So, not only there will be bulging and consequently internal crack, there also will be reheating crack on the surface. So, nozzle should be functional, they should use whatever water was intended to use, that means it should not get partially choked or totally fully choked. Number one is that I have mentioned earlier. Now, I am mentioning it should be properly aligned, that means the location should be such that whatever water we had intended to impinge on the strand surface, that should happen. It should not get obstructed or blocked because of misalignment. You see, because of misalignment, part of the water is getting blocked and only a portion of it is falling. So, in place of here you see, suppose what this is the range, normal range of impingement, normal area of impingement, you are getting only a partial impingement from the area point of view, also from the intensity point of view. Less area, less intensity. So, both are problematic, both will create difficulty, both will have problem. So, same thing I am trying to explain in a different, with a different figure. Suppose there is nozzle misalignment. So, what is the problem? The proper location is this, the dotted one. No, sorry, I am mistaken. The proper one is, this dotted one. So, in place of that, it has shifted this direction in this blue line. So, what is the consequence? There was some overlap. Now, because of shifting, here there is too much of water, and at this location no water at all. This is represented by this more blue area, means more water here, because it has shifted. So, too much of overlapping here and no overlapping here at all. So, less water here. So, what is the consequence? The temperature at this location will be more, at temperature at this location will be less. Again, here misalignment by just shifting, linear shifting. Here the nozzle has misaligned, but with an angle. So, what is the problem here? Similar, here at this point there is no overlapping at all, here there is too much of overlapping. So, that means at this location no overlapping means no water. So, the possibility of reheating crack is more. Here overlapping is there, that means too much of overlapping possibly. So, what is the problem? The temperature may be slightly lower. So, this is represented by, here you see too much of water, here you see too much of water, that means too much overlapping, here less water, here less water, that means undercooling. So, somewhere you have undercooling, somewhere you have overcooling. So, what is getting affected is the uniformity of cooling you are not getting. So, misalignment of nozzle can lead to non-uniformity of cooling. So, what is the consequence? I have told you what is the consequence. Certain areas wherever there was less cooling, you have more temperature. So, there is a temperature stripping, that means somewhere you have a temperature, high temperature. So, at these locations if the temperature of the strand is more, at this location if the temperature of strand is more, at the point of under overlapping, there is no overlapping, underlapping or no lapping at all, no overlapping at all or less overlapping, you have higher temperature. So, at those locations because of higher temperature you have possibility of reheating cracks, may cause cracks, may cause defects. So, I have explained to you if there is a misalignment, what are the consequences. Misalignment of nozzle means uniformity of water on the surface of the strand is getting affected. Certain areas you have more overlapping, more water, certain areas you have less water. You see, this area you have more water, this area you have more water, that means more overlapping, this area you have less water, this area you have less water, that means almost no overlapping at all or underlapping you can tell. So, what is the consequence? Consequence is because of that temperature differential on the surface of the slab at certain locations, and consequently there will be stress generation and finally there will be formation of crack, possibility of reheating crack formation. Now, let us come to another important concept, like when we are using secondary cooling, what control we normally do. Normally, conventionally, earlier it was amount of the intensity of cooling was tagged or tied up with casting speed. So, what was the situation? you know that when the casting speed is more, that means the shell thickness at a particular location is relatively less. So, you want more cooling. So, more cooling means more water. So, that is why if the casting speed increases, the cooling intensity also should increase. This was the logic initially people have been following for control of secondary cooling. That means, suppose you are using a speed of say 1 meter per minute, and another case you are using a speed of say 1.2 meter per minute. So, at 1 meter per minute, whatever amount of water you will be needing at different locations I am talking of, it is linked up with the speed. But when you go for higher speed 1.2, first important thing to remember is that at the upper segments you require more water, lower segments less water. So, it should systematically come down, because at upper segment cooling more cooling is necessary, because the shell is thin. So, you want thicker shell formation. How can it be done? Temperature of the shell should come down, then only thicker shell formation is possible, then only heat transfer will take place. So, at the upper segments more cooling, and slowly the intensity of cooling comes down as you go down, that is okay, there is no problem in it. But how much should be the cooling at any segment, that is linked up with the casting speed, because the higher the casting speed, more is the amount of cooling required, is it not? So, that is why earlier the conventionally the secondary cooling control strategy was to be linked with casting speed. But you see what is the problem, when casting speed is continuing smoothly, there is no change in casting speed during the continuous casting process, okay, this is okay, there is no problem. But suppose there is a, due to some reason that you have to control the speed, there is a possibility of say breakout formation. What happens? What do you do in that case? You bring down the speed, otherwise there will be breakout. To save that situation, you momentarily change the speed, and then slowly again you build up the speed. So, there is a decrease in speed and then there is an increase in speed. Because of this dynamism in the casting speed on the casting situation, what is going to happen? Say this blue line indicates amount of water flow, okay, these blue lines, forget about this for the time being, these blue lines. Then it was moving at a particular speed, okay, casting was going on at a certain speed. Now suddenly speed had to be controlled, so speed has come down, you see here. So, speed has come down, since cooling intensity is linked with speed, cooling intensity or the amount of water also is coming down. It is coming down, there is a gradient, it is constant, this is constant, then again it is coming down, it is coming down, then it is constant, okay. Then finally you realize that okay, now you have to increase the speed and go back to the normal one. What do? Again you increase the speed in steps and finally go to the original speed, say. So, what is the problem? Problem was this was the amount of water, then it has come down, and then again it has increased. But please remember, there is a lag between the speed and the amount of water, it does not happen instantaneously. So, what has happened here? You have decreased the speed, so it is also the water also is coming down, but what is happening here? So, that means the cooling possibly is maybe more, and then when the cooling has come down, then there is a possibility of reheating, that is whatever molten steel was there is trying to heat up, but that particular point of time there is a undercooling, because you do not have sufficient water to cool that. So, this initially there was overcooling, and then there was undercooling. So, whenever there is a casting speed change, initial casting being coming down and then is going up. So, there will be overcooling, there is undercooling. So, now what is the desirable intensity of cooling in such a situation? Desirable intensity of cooling is there will be a casting speed change. Casting speed change was necessitated by incidence of say breakout. There was an apprehension of breakout, that is why casting speed had to be changed. Intentionally we have not changed it. So, this situation might arise. So, what do you do in such situation? If there is a dynamic control, then it changes slightly beforehand. That means, when you are getting a signal that yes, now we have to change the speed, slightly beforehand you change the amount of water. So, this is what is happening. This amount of water is now following this path, this red one, and then when you get a signal that it has to, the speed has to go back again. So, before that you again increase the amount of water. So, this dynamic control is not linked with speed, it is a separate control. So, you can separately operate the cooling intensity. So, this is what is important to understand, that if it is mechanically linked with casting speed, is a mechanical conventional control is called. Cooling water intensity is linked with casting speed. So, consequence is whenever there is a change in speed, whether it is decreasing or increasing, there will be a lag, and there will be some amount of overcooling initially and then some amount of undercooling. So, what is desired is a separate control on cooling, not linked with casting speed. So, whenever you feel that casting speed has to be brought down, so before that you bring down the amount of cooling. So, there is a design how you do that, how much cooling you should bring down. Say you bring down the speed by say 10%. So, accordingly you have pre-designed, a priori you have designed how much cooling water should come down. So, cooling water you have controlled this way. So, you see cooling water is coming down, but there is no overcooling or undercooling. In case of mechanically linked water intensity with casting speed, there will be some overcooling, there will be undercooling. But for dynamic control, I am trying to explain, it is a different control, it is not linked with casting speed. Separately you can control the amount of water, and to what extent you know beforehand, because the speed will come down, you know beforehand how much it has to be controlled. You can possibly with the help of computer you can calculate that if I reduce the speed by say 10%, how much cooling intensity needs to be reduced. So, accordingly we do that slightly beforehand. So, that is the beauty of the system. So, it is called dynamic cooling. So, nowadays most of the caster operators are using dynamic secondary cooling rather than conventional mechanical secondary cooling, which was linked with casting speed only. So, here it is not linked with casting speed, it is separate control. So, it has the advantage of having no overcooling or undercooling, or even if there is very minor. So, what is the problem if you are overcooling or undercooling? If there is overcooling, as I have told you, temperature is coming down more than what is desired, and you are undercooling means temperature is going up. So, during undercooling you have tensile stress, during overcooling you have compressive stress. So, this sudden change in stress nature from say compressive to tensile will create crack, will create defect on the surface of the cast product. So, this is not desirable. So, that is why we need dynamic control of cooling, secondary cooling, rather than conventional control which is linked with casting speed. So, now let us come to a situation where we try to understand that what is going to happen when we are doing continuous casting. Suppose I have talked of misalignment. So, suppose there is misalignment of rolls now, I have talked of misalignment of nozzles. Okay. So, when there is misalignment of nozzles, then what happens? Cooling is not uniform. Cooling is non-uniform basically means there is generation of stress which can create either shape change of the cast product of the strand or crack formation. Now, suppose there is misalignment of rolls, what happens? You know what is misalignment of rolls? This roll, this roll, this roll, all three should have been in a particular line. Okay. This roll incidentally has gone up. That means from its intended position, the normal position, it has just moved up. So, what is the situation? Situation is because of this misalignment, you see this is a strand which is taking the shape because this is supporting the strand. If the support itself is getting shifted, the strand also will get shifted, and because of this there will be a generation of strain. So, this is called roll misalignment strain, say epsilon m, I have designated it as epsilon m. M indicates misalignment, epsilon indicates strain. So, there is a strain generated because of misalignment. Now, in between the two strands, I have told you there is no support. So, particularly in the upper segments where the shell thickness is less and depending on certain grades of steel, you know, when the shell strength is not much, say very low carbon steel or silicon steel or say ferritic stainless steel, the strength of the where the phase is ferritic, strength is not much, the shell thickness is not much at high segment zones. So, there is a possibility of bulging. So, if there is a bulging, then also there is a strain. So, it is called bulging strain. We have designated it as epsilon b. Now, I have told you that there is a possibility of bending of the strand. When do you bend it? When you are using vertical mold. So, the strand which is coming out from the mold is vertical. Now, from vertical we have to give it a bend to curve it, to make it curved. So, there is a bending. Now, how is it done? Because the rolls, the orientation of the rolls are getting changed, the segments are getting changed. So, there is a stress generation on the strand, but as I have told you, it is not done suddenly. You have to give a slow orientation change in the direction, so that the amount of strain is less. Nevertheless, there will be some strain. So, that is called bending strain. And also finally, when there is a curved strand, we have to make it horizontal. The only way out is we have to straighten it. So, it is called unbending. So, again there will be an unbending strain. So, there is a unbending, there is a bending and then unbending. So, it is called UB, unbending, bending, strain. So, the total strain on the strand, if you now add all these three, is a combination of bulging, combination of misalignment if there is a misalignment of roll, and then there is a bending, unbending. So, all these three together will give us what is the final strain, and this total strain, as I have explained earlier, should not exceed the critical strain limit for every steel. Every steel has a critical strain limit. It depends on what type of steel. If the sulfur content is more, we know it is more prone to crack formation. If the phosphorus is more, because the shell is thinner, so it is also there is a possibility of crack formation. So, depending on the type of steel, it is prone to different type of crack formation. Now, this strain, total strain which is getting impinged on the shell, solid shell, should be less than the critical strain, otherwise there will be crack formation. If the particular steel can withstand strain to a large extent, it is very good. Even if there is a possibility of large strain formation, there will not be a crack generation. This is number 1. Number 2 is strain rate. I have explained to you earlier also that like strain rate also is critical. Like the same amount of strain we are giving suddenly, say bulging strain or say bending unbending, it will be easier to explain bending unbending strain. Bending unbending strain can be given suddenly or can be given slowly, depending on how slowly you are changing the profile of the strand. If it is a slow change in profile, the strain rate will be slow, and if it is a sudden change in the profile, that means one particular roll and the next particular roll, there is a lot of angle between these two rolls, we call it a sudden change. If it is sudden, it is quite large, then the strain rate also is more. So, the strain is important, strain rate is also important. Strain rate also should not be very high. Now, strain rate for all these three can be separately calculated. Strain rate will be due to bulging, strain rate due to misalignment, strain rate due to bending unbending. So, all these three together will give us total strain rate. So, total strain should not be much, total strain rate also should not be much. So, these two should be less than the critical limits for a particular steel. When we are in that range, then we are safe, the chances of crack formation will not be there. So, while we are operating continuous casting, we should remember, because strand is very important for secondary cooling, I have told you how the strand is operating out, what is the strand radius, whether it is changing suddenly, the radius is changing suddenly or it is smooth. These are very important parameters. These will give us control strain and control strain rate. Now, let us try to understand another important thing. I have told you the purpose of secondary cooling is to reduce the surface temperature of the strand, that is the purpose. You are doing secondary cooling because you want to take out heat which is there inside the strand, which is which is there in the molten steel, locked up in molten steel, that heat you have to take out. So, that is why you are doing secondary cooling. So, secondary cooling basically will take out the heat. How it will take out? It will lower the surface temperature of the strand, and because inside molten steel temperature is high, so there will be a heat path from inside, heat will coming out. So, this is dictated by what is the surface temperature. Now, intensity of cooling and uniformity of cooling I have told you several times is very important. Now, the intensity cooling will give you or tell you along with the speed what is the temperature at a certain location of the caster, that means at a certain location of the segment when you are coming down. What is the temperature, surface temperature, and if the surface temperature is known, you know what is the temperature inside also, there is a pattern. So, this is dictated by secondary cooling. Now, I have told you earlier that there is a low temperature poor ductility region in steel for all steels, and for microalloy steels this is quite high. This low temperature is quite low, this the ductility is quite low at certain temperature. Now, what is that temperature? That temperature is around 800 degrees centigrade. Look at this, the ductility in the form of reduction in area has been plotted with temperature. So, this is the temperature and this is the reduction in area. So, just let us see what is happening. For plain carbon steel, the green one, ductility is coming down but not to that extent. So, at around 800 it is coming down by say 10% or 20%, which is not very harmful. But look at, you have a vanadium bearing steel, this red one, it has come down to say 50% from 100%. We have vanadium variety of steels, it has come down to less than 50%. So, this temperature for this particular microalloy steels is very sensitive. That means, we have to see to it that when the shell is getting cooled, the strand is getting cooled with the help of secondary cooling, we have to avoid this temperature region from 700 to say 900. More than say 900 to 1000 it is okay, because the ductility level is high. Less than 700 also it is okay, ductility is high. So, this temperature, that means 900 and above is okay, is safe, 700 and below is also okay, but between 700 and 900, particularly say 750 to 850, we have to be very, very careful. Why? Because at this temperature the microalloy steels have very low ductility. So, what is the problem? As I was telling you, whatever strain are getting generated and whatever strain rates are getting associated with that strain, if that is above a critical level, there is a crack formation. So, what is happening here? The ductility of the steel in the form of reduction area is getting affected. So, that means these microalloy steels, you see, they are more critical than plain carbon steel. These microalloy steels, they cannot tolerate temperature in the range of say 750 to 850. Plain carbon steel, okay, it is okay, maybe it has just come down by 10 to 20% ductility, but microalloy steels, the reduction in area has come down by to less than 50%, and minimum 50% is normally taken as a safe reduction in area for operating continuous casting process. That means, whenever the reduction area comes down below 50%, there is a possibility of crack formation, because the steel cannot, some strain is always getting generated and there is some associated strain rate also. So, these together are creating problem for the steel, but if the reduction in area for a particular steel is having more than 50%, then those strain and strain rates can be withstood, can be tolerated. But if the reduction area is less than 50%, then we have to be careful. So, we find the temperature range of say 750 to 850, this reduction area is quite low, lower than 50%. So, that is why these microalloy steels are very difficult to cast, they are prone to crack formation. So, what is the way out? Way out is we allow secondary cooling in such a way that this particular area is avoided during continuous casting. That means, either you do soft cooling. So, soft cooling means when the solidification is complete, the temperature is say about, then solidification is complete, the unbending is over. So, it is becomes horizontal, there is no chance of any strain formation. So, the temperature is not coming down to less than 900. So, this is a safe zone. Or you use hard cooling, so that temperature goes to less than 700 or 750 very fast. So, you can avoid this temperature region, or you do low casting. So, low casting is, how does it help? Low casting help in getting very low temperature. If the casting speed is low, then the surface temperature of the strand is also relatively lower. So, that means you are not allowing too much of strain formation in these particular grades. So, there are two strategies, either you do soft cooling or you do lower casting. Then only you can have a crack free microalloy steels. So, the secondary cooling technology these days, there is a possibility that you can control it. The width control, I was talking of width control, how much of cooling will be there. Let us look at it here. Yeah, spray width control, that means you can intentionally switch off certain nozzles, you do not allow cooling through those nozzles. So, what does it happen? So, the width of the spray width is you can control, intensity you can control, width also you can control. So, with the help of these two controls you can have desired surface temperature on the strand. Surface temperature of the strand control means inside also we have a control. So, with the help of this control you can get either relatively lower temperature, that means less than 700, or you can have relatively higher temperature when your unbending you have complete. So, you do not allow the unbending region or the straightening region to have this temperature, because unbending means the strain will be there, bending unbending strain. So, you do not want strain to get generated when the ductility of the material, reduction of the material is low. So, that means you do not do bending unbending when the temperature is in this region, you do either here or there, either at higher temperature, that means you have to use soft cooling, or you do at low temperature, that means you are doing low casting, low speed casting. So, I have tried to explain that how with the help of proper secondary cooling you can have a better quality of cast product. So, I have told you what are the problems. Problem is secondary cooling should have from the bottom of the segments, that is at higher segments, that means just below the mold you should have relatively more cooling, and this should systematically come down, not suddenly it should come down. Suddenly come down, suddenly going up is not good. Uniformly it should come down systematically as you are coming down the segments, number 1. Number 2, uniformity of cooling is very important. By uniformity of cooling I mean throughout the edge, throughout the surface rather, it should be uniform. That means the nozzles which are using water sprays, they should not get choked or partially choked or fully choked, or they should not get misaligned. If they are misaligned, I have explained what can happen. There will be certain areas there will be more cooling, certain areas there will be less cooling. So, non-uniformity of cooling will be there, there is a possibility of stress generation, and consequently this will result in crack formation. So, uniformity cooling is important, slow cooling is important, throughout the width of the slab and throughout the surface of round or bloom or billet it should be uniform. Particularly for bloom or billet, one surface should not have less cooling compared to the other 3, then the shape also will change. So, for getting a uniform shape, for getting good quality, that means absence of cracks, uniformity of cooling is very important. So, all nozzles should work properly, there should not be any misalignment, there should not be misalignment of rolls also, because there is misalignment of rolls, there is a possibility of again stress generation. So, the whole segment should be properly controlled, we should do systematic overhauling of the segments after certain hits, whether all the segments are proper, whether all the rolls are proper, whether there is misalignment or not in the nozzles or on the rolls, all these things need to be properly controlled. So, I have tried to explain how secondary cooling is important, what are the precautions we have to take, then only we should have good quality of material, cast product. So, uniformity of cooling, systematic cooling is very important. then only we have a crack free and other problem free cast product, and also the shape will be uniform. Thank you very much for your kind attention.